So, the problem today we will do is load balancing. So, in the load balancing problem, what are we given? So, this is a very fundamental scheduling problem. Okay. So, you are basically given n jobs, okay, and they have some processing time. Okay. So, n jobs and they have a processing time, say P1, P2, Pn. Okay. And now you are given and then m identical machines. Okay. M identical machines. Okay. So, what is meaning? So, like power, strength, everything of these machines are same. And what is your objective? Your objective is to assign jobs to machines, okay, such that what happens is to minimize the time taken for the last job to complete. Okay. So, to minimize the time taken for last job to finish. Okay. Or in other words, basically what I am looking for is a function from jobs, say job, there are n jobs, okay, and I have machines M1 to MM machines. Okay. So, I am looking for a function from here such that what I want to do is that I want to, so either you can think of this. So, if you think of this, this is basically partitions of job, right. So, this is basically partition of jobs into S1, S2, Sm, right. So, this is processing time. Okay. Okay. So, this is okay, this is a partition this of n jobs, and what is my goal? My goal is to minimize maximum over I going from 1 to n P of Si. And what is P of Si? It's basically nothing but you sum over j in Si processing time of j. So, if a some job j is in Si, look at its processing time, this is it. So, I want to, so think of this way that I have machines and I am assigning jobs, jobs, right. So, how much time it takes to finish? So, you just sum the total time it takes for each of these jobs to here, okay. And what I want to do, I want to minimize the maximum amount taken by any machines. Okay. So, that is the question. Okay. So, I want to partition my jobs on these machines such that the maximum time taken by, so the maximum time taken by the any machine is minimized. Okay. Is the question clear? Okay. So, I am sure you all have seen several algorithms for this in, it's there in Klein-Bertardos. Okay. So, there is no point telling me answers. Okay. So, I will tell you, I will give you an opportunity where you can tell me your answers when we reach there, okay. Because now you will tell me, oh, do this, do that, I understand that, but this is something which you must have been taught or learned in the first basic algorithm course. At least I taught in the algorithm course to someone whom I taught, I really do not remember which batch. Okay. Okay. So, this is a very fundamental problem, and this problem was studied way back in 1966 by Graham, okay, by Graham, okay, way before when NP completeness and all these kind of things were even discovered. You understand, right? So, this is like you, if you have seen algorithms for bin packing or knapsack, some of these kind of things, it is of that flavor that you are trying to partition objects, okay. And there is a most obvious algorithm for this problem is known, what is called list scheduling algorithm. You just basically imagine yourself that you have some set of machines at any point of time, and I give you some job, right? So now imagine that I want to make an algorithm. So the way these things happen actually is that this is one when jobs are given to you. Imagine that these jobs are not given to you in like you don't know these jobs. Okay, the jobs are coming one by one. Okay, so you have these machines running. These are machines which are running. Okay, these are the machines which are running at this point of time, and this is what I mean. Oh, this is the current processing time of this machine. A new job comes. Okay, and now you need to allocate this to one of your machines. What will you do? You understand what I'm saying? My question is, there will be some n jobs, but you have not seen these jobs. They are coming one by one, and the moment you have to, it comes, you have to make a decision where to, allocate it or where to schedule its processing. So what will you do? Now it's time for you to answer. Huh? Okay, right? Okay, so the basic heuristic will be is that at any point of time, assign the job to the machine which finishes first. Okay, so for example, here where should I allocate them? Just to make it distinct, where should I allocate them? Probably here, right? So maybe something like that. This can happen, right? So this is my current heuristic, right? So I'm assigning job to the machine which finishes first at this point of time. So at any point of time, when a new job comes, I can do this point of time. Okay. So this is basically, this is what is called online load balancing, right? So what is an online problems? So in online problems, objects are coming one by one, and you have to make decisions which are not changeable later. Okay. If he wishes to join.
That's what he was asking. Is it okay if he joins like in the middle of the course?
Of course. Anybody in the world can join. Okay. So we are going to assign to the job to the machine which finishes first. So this is a very model of an online algorithm where your work, like items are coming and you have to make a decision on the item then and there, right? And these decisions are not reversible, right? And you have to maintain certain, like if it is a hard problem or even easy problem, you have to maintain certain ratios, right? For example, if edges are coming and I wanted to compute a matching of my graph, right? So when edges is coming, I have to make a current decision whether to add it to my matching or not, or let this edge go. You understand my point, right? So these are the model which is of the online algorithm. So lot of things happens in web and this, they are actually online. Okay. Okay, so we will not worry about online, but this is a model which you should be worried about. So, and what is good thing, if this is the kind of online algorithm, then as far as you remember, this is the best algorithm that you can hope for. Okay. Okay, so here's my algorithm. Let's write it down. Okay. So here's my procedure. It is called list scheduling. So you have n jobs, processing time, right? And m integer, which is basically tells us the machine. So what it basically tells us, consider jobs in any order. Okay. So in any order, it doesn't matter, okay? And this is what I will do. For each machine I in M, maintain load I okay, initialized to 0. Right? So, I am maintaining what is the current load on the machine. What is load? Basically, sum of the processing time of jobs that are allotted to the current machine. That is the processing time of, or that is the load of machine. And in the term of load, my goal is to minimize the maximum load. Okay. So, now for j equal to 1 to n, what I am doing? Okay, find machine I with least load, right? Least load, assign j to I, that is set sigma j equal to I, right? So, I am assigning the jth job to machine I, okay? That is it. And what is the load of I now? It is load, current load plus the processing time of the jth job, okay? Return sigma, that is it. So, this is the end of my algorithm, right? So, basically whatever I said is this is an algorithm, okay? And whatever we are going to show that this is basically returns a factor 2 approximation. So, what is the best factor approximation you have seen for load balancing? You have seen any approximation algorithm for load balancing? No? Okay. So, what do you think? Imagine yourself a buckets of water, like some cans of water of different kinds, right? What will happen? And so, imagine you have 10 big places to hold this water, and you want to be as uniform as possible, right? How much difference? And when your bucket comes, you go to a big bucket which has the least amount of water. You just pour into it, right? Have you ever played this game? I was playing with my son few days back, like we pour, and you can show that. Okay. Okay. So, of course, I can make it mathematical, but look at this picture. Look at this picture. Imagine that this is the in the current setting, which is the which machine takes the worst time? Huh? Which machine takes the worst time? Which one? This machine, no? Right? Okay. But notice, suppose this is the machine which takes worst time. Now, at any point of time, look at why does it take worst time? Why does it take worst time? Because at that point, or why did you assign this to his? Because at that point of time, if I draw a picture, every other machine were taking more time, like the processing time. That's why I put it here. Okay. So, this is the picture to keep in head. Okay. If you all the time write, then how will you follow? Why did I assign this to this machine? What is the definition of why did I assign this?
Because this machine has the least.
Yeah, it means every other machine is currently taking more time. That's it. That's all that I said. trying to write everything I say is not an optimal thing. The best way to learn is take basic set of notes and go and expand it with the help of videos when you want, and try to understand what was the arguments that was made here. Otherwise, you are going and repeating because you have only concentrated on taking notes, right? When you go back, you have no memory of the arguments, right? So, the best is I write my lemma, I write my this thing, I write one or those two ideas, why did that lemma proved, and then go and try to expand it at the end. You understand? That's the best way of learning. Else, it is very hard to keep focus of what is, why something is happening versus taking notes. So, this way it's called taking notes, it's not scribes. Scribes is something where people should go and expand it everything, right? So, you should try to write notes, not scribes in the class. That's the basic difference you should take. Like, what are the basic things that you should know? You also have now ability to take pictures. So, take pictures and write down what is the basic reason why something happened. That will help your post processing time much lesser, but it's up to you. Okay. Anyway, so this is how the world looked like. That when I did this, everybody else was taking more time. Okay. So now let's try to understand what happens at this point of time. At this point of time, some items were scheduled here, some items were scheduled here, right? Some items, some items, some items, some items, some items. If I delete this, item, then what happens? The processing time of every other machine can only be larger than this machine, right? If I delete this item, then the processing time, the load of every other machine, so suppose this is a load I at this stage. So this is the what is it called? This is a job which makes I take longest time. Okay? Like this is what makes this, right? So when I added this, every other processing time was larger. Is that even at that stage? Even after this, if some more items are coming, maybe they are scheduled here, maybe they are scheduled here, but the processing time on load of these things is strictly more than the load of this without this item. Is that fine? Right? Because even without this, the load of these people, load of these machines were larger than the load of this I. So if after that, if I add more things, load can only increase, it cannot decrease, of course, without this, right? So that's all that is required to prove this, that this is a factor 2 approximation. But to do that, let's get some basic lower bounds. So what is first basic lower bound? L1. I want to write. What is the, like definitely this algorithm will take at least this much. Can you say one number? L1 is that's it, right? So this is definitely whatever happened, max of pi, like any optimum solution, opt, right? Opt will at least take max of this time. Is that fine? Because you will assign that individual job to someone, no? Okay. What else? What about average? This is also true, no, right? If total time taken by all the jobs is summation pi, at least one of them will take at least divided by m, pigeonhole principle. That's it. So opt is greater than equal to L, which is max of L1 comma L2. Is that fine? Right? So we will just work with these two basic lower bounds on the opt, and we will be able to prove this. Okay? Is that fine? Okay. So let L be the job that finishes last. Okay? So for example, this is a job I'm talking about. Okay?
Okay, why max of L1, L2? Because L1 is greater equal to L2 always, right? Because maximum will be greater equal to average.
Why?
Because otherwise maximum is if less than average, then all are less than average. Then how can the sum be?
Okay.
There is no point. I mean, okay, no, I'm saying max of L1, L2 is always L1.
Fine, but it's okay. Right, you're right. This would all, I mean, I could use from there also. Okay. So now look at this machine I. Let X be the other jobs assigned to machine I. Okay? Okay. So what is P of X? What can you say about P of X? Right? So what is the algorithm returns? Algorithm ALG is nothing but P of X plus P of L. Right? Because what is it? This is basically all I'm saying to you. Look at this. There are some other jobs that have been assigned to this. So how much time those will take? P of X, and the time taken by the last item is P of L. And since algorithm returns you this load, this is the maximum load. This is what by definition this is the maximum load. So algorithm returns P of X plus P of L. Returns what is the load of this list scheduling algorithm? It is time taken, summation of the processing time in X plus processing time of the last element, P of X plus P of L. Is that fine? You don't understand?
What was the number L? L is the last job that
Let L be the job that finishes last. This is the job that finishes last. So now it means this machine takes the longest amount of time, right? So I'm saying this is because after this, am I assigning anything to this machine? No, because we are done. Because, okay, so if I delete this, so what all items are assigned to this? The item which are assigned to is X union L. So the total time taken by this item is processing time of elements in X plus processing time, and this by our definition this is last. So that is what algorithm returns. So the mix span or whatever we want to optimize, this is what algorithm returns, and we have to relate this algorithm with the optimum cost. Okay. So because of the red line, what is the meaning of this? Can I say load? So if this is a machine, say I, load of j not equal to I is greater than equal to P of X for all machine, right? Is that right? Because at this point of time, X was allotted to it, and when you were making a decision about this, it had some load, right? And later maybe some more items can be added. So at the end, whatever maybe the load of other machines are, it is definitely load is more than P of X, otherwise we would have assigned that item. Is that fine? Of course, if this will be equal, then you can assign it to arbitrarily, but that's perfectly fine because I'm only writing greater than equal to. That's all that I need. Okay, so then we are done. Okay. Okay, so okay, so now
But in this example, it can also happen that it is not taking the largest time.
meaning
Like when we add this one, maybe it is taking less time than the other machine. Means this is not in any order.
it is not in any order. So read. Let L.
I understand.
Huh?
But for this one, that PL,
Huh?
so PL can be small also, no?
It can be. PL is not the.
The time. I am saying suppose it is less than the below one.
I do not understand what you are saying.
Okay.
Wait, please. Let me. What are you saying?
It is taking this much time and it is taking the time and it is exceeding everything else. I am telling that it is not exceeding. It is less than the other current time. And suppose the load of the other machines is so much higher that after adding PL also, this machine still takes less time than.
But this is not about that. Like, please, first let's read. Let L among, so I have done my algorithm. Algorithm is over. I have assigned n items. Okay. Now, let's look at, is the first job finishes last? Second job finishes last? Third job finishes last?
Oh, finishes last, not the adding thing. Okay.
Let L be the job that finishes last. Right? This is the job. I am not saying this is the last item that I have added. This is this is a job that finishes last.
Not the last assignment. Okay, got it.
This is not the last item in my order. Okay? This is all that I am saying. I mean, this is exactly what I said. If you have listened, after this, many more items will come and they get added, and hence load can only increase. This is why I am saying all this. Otherwise, what's the point of saying that? Okay? So now, if I add, what can I say? Summation of load, load j, okay, j going from 1 to m. Let's sum this load. This is, can I say this is greater than m times p of x? Is this correct? Load of each machine is at least p of x. So this is definitely m times p of x. But what about the load of I? Load of this guy, right? So if I look at the load of this guy, so look at so load of this guy is something, load of this guy is something, but actually here we can save something. This is definitely correct, right? What is this? Because on the ith, is also px plus something, right? So in fact, I can write here minus pl and still this inequality holds. Look at this. What is its load? Its load is this p of x plus this. So I am only talking about p of x. So from this machine, I can say pl. Is that fine? Yes, no. Look, load of this is at least. Do you have a question, Sushmita?
No.
Okay. Right? So because what is the okay? So what can I say about all this? Right? So this is p of x. P of x is less than equal to what? P of x is less than equal to summation j equal to 1 to m load j 1 over m. Is that right? Minus pl divided by m. Is that fine? I divided m here. Okay. What is this quantity? Is L2. This is less than equal to L2. And what is this quantity? What is PL? Is less than L1. So this I can write 1 over m times L1. Is that fine? Why? It can only be larger. You have to subtract at least this much.
Shouldn't L1 that is L1 is greater than PL, right?
What?
That says PL L1 is greater than PL. Over here you have a negative sign.
Okay, fine. You are right. Okay, so I shouldn't do this. Okay, fine. Okay, so let's do one thing. We'll get there. Let's add PL here. Let's add PL here. Both sides. Is that fine? So what is this? This implies algorithm is returned by, what is this load? What is this load? 1 by m, this is L2
It's like average, yeah.
minus, now I can take PL common, and 1 minus 1 over m.
Now L1.
Okay. This is L2 plus 1 minus 1 by m times L1, and I know these are there, opt is at least this much. right? So what I'm getting? So I'm getting here, this is less than equal to 2 times 1 over m times opt. Because L2 is less than equal to opt, L1 is less than equal to opt. So if I take opt common, it is 1 plus 1 minus 1 over m, so it is 2 minus 1 over m. Okay. Okay, that's great. Okay. So what we have learned is that this algorithm is actually not only factor 2 approximation, it is 2 minus 1 by m approximation. So if the number of machines is like 1, then this is optimum. That's great. If it is 2, then this is 3 by 2 approximation, right? Okay, great. Do you think this algorithm is tight?
It's weird. So more machines, its performance could fall. It would get very close to 2.
Yes.
Fewer the machine you are mimicking opt.
Only for one.
Yeah, one machine it's like
You have no choice.
there's no choice. Yeah.
Okay. Anyway, but is this algorithm tight? Right? Can I improve can I improve my analysis without changing this algorithm? You understand my question? Okay. So unfortunately, the idea is no, we can't. Okay. Okay. Unfortunately, the idea is no. Why? Because imagine yourself that I have okay. So I have m minus 1 jobs of processing time 1, and I have 1 job of processing time m. Okay. So how much time will this take? You might ask, what is the
Unit length jobs.
yeah unit length jobs? Wait. So we have say m into m minus 1 jobs of length 1 and 1 job of length m. Now it is to be done in any order, right? It is to be done in any order. So imagine I try to do it for the, so this is job, this is machine 1, machine m, right? So if I suppose I process in this way, what will happen? Is that correct? This is how I will fill it. And finally, how many times I would have filled it this column? Okay. And then the last guy comes, right? He will be somewhere here. Okay. But what could I have done? And the rest, right? So this can give you a factor 2 approximation. That's all that I was trying to give, right? Okay, but let's look at the analysis. Okay, I would like to look at the analysis and try to understand what's happening. Okay, so is this example clear? So this particular algorithm cannot be improved, right? That didn't mean that we cannot get an algorithm for the problem. Okay, so let's try to understand. Okay, so keep this analysis. This is all that analysis we will do in for next 2-3 hours. So just keep this analysis. Okay, the rest is mental maths. Okay. Okay. So and all I need to use is these 2 lower bounds. Okay. 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 Let's see. I want to zoom ourselves at this, right? I want to zoom ourselves at this. Okay. So this algorithm has alg is less than equal to opt plus, because this is less than equal to opt, and then we replace PL with opt. But I do not want to do this for now. right? If I can say that, hey, PL is less than equal to opt by 2000, then what can I get? If I showed you that PL is less than equal to opt by 2000, what approximation factor do I get? Then I will get this is less than equal to opt plus 1 minus 1 by m by opt by 2000. So, this is if I take opt common, right, then I will get 1 minus 1 by m plus 1 over 2000. No? Why not? Why not, Sushmita?
It will be multiplied. If you take opt out, it's 1 plus 1 minus 1 by n into 1 by 2000.
Okay, fine, you are right. So, it should become 1 plus 1 by m by 1 by 2000. Does it give a better approximation for us? It is, right? Because I can forget 1 over m, because this is minus.
If m is larger than
It doesn't, no, Sushmita, for m, just forget it. It is 1 minus 1 by m, it is less, right? So, what happens? So, I can definitely write this is less than equal to opt 1 plus 1 by 2000, which is great.
So, what is m here? 1?
Doesn't matter.
It's just an upper bound. Okay.
1 minus 1 by m is replaced by 1. Okay, this is 1 times this. Okay, so this is it. So, if I had a better upper bound on my last finishing item, then I could have improved my approximation factor, right? Okay. So, that should tell us that maybe we should not consider this job in any order, but in what order? Largest job first, right? Okay. So, this is how. But notice, but then this algorithm will not work in the online fashion, because I have not seen all the jobs, right? So, what is the notion of largest or this? So, if we are in a static setting where all the jobs and their processing time is available to us in the beginning, then I can make this decision, right? But when it is not given to us, when we have to make decision as and when the jobs are presented to us, we cannot do any of these rules. You understand? Okay. Okay. So, now as all of you are saying, okay, so rather than consider jobs in any order, consider jobs in like with what is called LPT scheduling or greedy scheduling. Okay, and this is called based on LPT rule or longest processing time first. Okay. So, these jobs are ordered in a way. So, consider jobs in the following order. Okay. P1 is greater than equal to P2 greater than equal to Pn. So, I am now not considering them in any order, but I am considering them those items first whose processing time is largest, and then so on and so forth. That is the end of my algorithm. Okay. Now, notice that the example, counter example that we made, it goes away, because first now this algorithm will fit that m and then try to fit other people, other jobs, right. So, at least that counter example is dead and dusted. Okay, but let us try to make what good this approximation could, like can it give optimum, or can we come up with an example where this will also do bad. Okay. 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 So, imagine that I have a following sequence of job. I have 2m plus 1 jobs. Okay. 2m plus 1 jobs. Okay. 2 jobs of length m plus 1, m plus 2, so on and so forth. Okay. So how many jobs did we get? 2 jobs of m plus 1, m plus 2, up to 2m minus 1. So how much we get? I think we are done with 2m and 1 job of length m. Suppose this is what happens, right? So first what will you process? First you will process these things, right? What will happen then? What is the ratio here? 2 jobs of length m plus m1, m plus 2, 2m minus 1 each. Okay, and 1 job of length m. So what will happen on this? So what will happen? Notice first of all that first this will be assigned. So think of this way. So let me draw a picture. So what is going to happen? Right? So what I mean? So first this is a job of 2m minus 1. Next you will assign 2m minus 2, right, on the next machine. And the last will be right, 2m minus 1. That, okay, so this is going to be, so let's bunch together. So this is going to be different staircase. Okay? Then this, and then this, so on and so forth. Is that fine? Okay. But what will I get at the end? I have m, right? So, and finally, where will this m will go?
Where it is the minimum. Not the last, why should the last? It is the where it is minimum, like kind of thing. Like which machine is taking minimum now?
So what is the minimum it will take? Let's understand, no? So how many let's look at how many jobs are here of this length. Let's see, 1, 2, m minus 1, right? Into 2. So what happens? And I have only m such objects. So now notice this is, right? So after some point of time, after I have done with m, I will start getting these jobs like this, right? First here, then here, right? And I have 2m plus 1 job, right? So all these jobs will be like this. But the mth job, the m will be where? Somewhere here. Right? Because this you will get what? At the end you will get something like m plus 1. So how much did we get? It's like some 3m plus 1. And then this, and if you notice, everybody will be like 3m plus 1. Right? Because this, and then one job of a, look, I'm coming from here, then I'm coming something from here. You will, so for example, what will I get here? I will get another. So imagine that everything is power of 2, m is also power of 2, and everything. So like it's even number. So if I do this here, what will you get here? So what is the total?
Yeah, the last machine will get 3m by 2 at job. With 3m by 2 minus
What will the last job, this machine will get?
3m
So
by 2 that job.
yeah, and
You go back up. Yes.
so
You are pairing, right?
yeah, so this is exactly. So I'm saying that everybody, if you notice here, like on any machine, it is going to be something like 3m. Okay, and then this one m guy will come at the end, which will be. So what is the approximation ratio for this? You understand my question? Okay. So show that this is 4 by 3. Okay. So you can show that this is 4 by 3, and I'll leave that as an exercise for you. Okay. It's an interesting exercise. Okay. Now, if you look at the book by Kleinberg-Tardos, they give you 3 by 2 approximation algorithm in that book. Okay, which is slightly easier. So now I want to go further, and I want to do first 4 by 3, and then I move ahead, and like that's not where I want to end in the class. I want to give what is called polynomial time approximation schemes, or actually efficient polynomial time approximation schemes. We'll get there. Okay. But notice, if I wanted to show that this algorithm has 4 by 3, then if I show that PL is less than equal to opt by 3, am I not done? If I show that PL is less than equal to opt by 3, then what I am going to get? 1 plus 1 by 3, which is equal to 4 by 3. So, somehow if I could re-engineer my analysis in a way that this happens, this is great, right? Okay. So, let us pretend that this algorithm has 4 by 3 approximation, and let us try to see where we fail. Let us try to prove inductively that this has a 4 by 3 approximation. Okay. And then of course, we will fail, and then we will fix that up, or we will hurdle. Okay. So, but you notice it does not matter which order I did. So, this is a particular order. So, whatever analysis I did for the first algorithm, everything holds, right? Okay. So, all I have to care about is the PL is not too large. The last item that finishes is not too large. You understand? Okay. Okay. So, let us try to do. So, what is the lemma I want to prove, and this will also tell us a little bit more about how did this. So, here is a theorem that I want to prove. Okay. So, the theorem I want to prove, greedy produces 4 by 3 factor approximation for load balancing. Okay. This is what I want to see. This is what I want to prove. Okay. Let us try. Prove induction on number of jobs n equal to 1. Base case, definitely there is only one job, you are definitely producing opt, so it is 4 by 3, right. So, let us assume that the number of jobs n is strictly greater than 1. Is that fine? Okay. So, let me do the analysis. So, now we have some n jobs, and I want to see what happens. Okay. Then you will see where we will get stuck. Okay. So, I do the analysis as before. Let L be the last, let L be the job that finishes last. Okay. For her, let us assume L is strictly less than, the last item is less than n, like what do you call GL. Okay. So, L is strictly less than n. So, it is some item here which finishes last, not the last item. Then I will be done. You understand? Imagine that among, I am following this order, and I say, hey, look at some PL, this is the guy actually finishes fast, it is not the last item. What happened? Are we done then? I delete the last item, I have smaller number of items, right, and I have only removed the last item. So, sorting of these numbers remains the same. So, if my scheduling algorithm will work, it will give me, now I go and add back, anyway it is not increasing anything, so I am done. Okay. So, this is why you do not care about the last. You can always assume the last item is nothing but nth item. Okay. So, if L is less than n, consider jobs 1 to n minus 1, right. Now, what is the property? This is in this order, right. So, now you are going to work on 1 to n minus 1 and n. Now, are the number of jobs strictly less than previous time, right. So, by induction hypothesis, greedy returns 4 by 3 of what? 4 by 3 with respect to job 1, job 2, job n minus 1. Okay. Right? Greedy returns me this. Right? So, the schedule which, So now nothing. So what is the property of the schedule? Let L be the job that finishes last and greedy return you sigma. So it's basically I can run whatever I ran before with this, and now basically whatever you return that has 4/3 approximation, and when you add the last item it goes and attaches somewhere else. So it never matters. Okay. So this is, do it. Okay. This is not interesting part. Okay. So I'm not going to do this. Okay. So what is interesting? So the interesting part comes, and this is where the analysis will take us. Okay. It's on purpose left for you to fill the gap. Okay. So now L is N. So the item which finishes last is the last item. Okay. Now if Pn is less than equal to opt by 3, we are done. If Pn is less than equal to opt by 3, we are done. So now what do you know Pn? And this is the case we don't know how to handle. This is the case we don't know how to handle. Right? So now let me tell you the basic set of ideas. This is where I will go start working now. Okay. Okay. Now let's start. Look, we don't know this opt, but it is only for the analysis. It is not for the. It is not for this. So all we have said, if this would have been the case, the algorithm returned you 4/3 approximation. If this is not having the case, still algorithm returned you 4/3 approximation, and then hence you are good in both cases. Okay. Okay. So you understand what I'm saying? If Pn would have been less than equal to opt by 3, algorithm anyway returned you 4/3 approximation, nothing to prove because of the same analysis. So let's assume that even when Pn is more than opt by 3, actually algorithm returned factor 4/3 approximation to us. Okay. So now here comes the idea which is transcendental in any of these things. So I define, I don't know this opt. I say, okay, I define the notion of big jobs. So what is the meaning of big jobs? Those are the big jobs. Big jobs, it means J, Pj is strictly greater than 2 times opt by 3. Okay. Processing time is more than 2 times opt by 3. Those are called big jobs. Then I have a notion of medium jobs. Those jobs where Pj is strictly greater than opt by 3 but less than equal to 2 times opt by 3. So these are medium jobs. Right? Okay. And what are small jobs? Remaining. J such that Pj is less than equal to opt by 3. Is that fine? So this is how I have divided my jobs. Again, it is for the analysis. We don't see these things because we don't know opt. If we knew opt, then I can see all these things. Okay. So there are big jobs, okay, and there are medium jobs and there are small jobs. Okay. Okay. Now I'm going to rub these part because there's nothing in this algorithm. Okay. Okay. And there was nothing in this analysis. Okay. Okay, excellent. Okay. So I'm going to define n big number of big jobs, n medium number of medium jobs, n small number of small jobs. Okay. This is, so cardinality of this is n big, cardinality of this is n medium, cardinality of this is n small, right? Is that fine? And so NB, of course, is equal to n, right? Because every job is partitioned into this, this, this. Okay. And we have m machines. Okay. And how many machines we have? M machines. So let's do some pigeonhole principle kind of methods. So we don't see, but opt, definitely opt is scheduled, right? Like there's a best scheduling where the total amount of time taken by any machine is at most opt. Do you agree to that? Okay, so right? Okay, so this is like schedule with max load equal to opt. Please tell me how many big jobs can we accommodate on one machine? Huh? At most one, right? On any machine we can at most accommodate one big job, because this is a schedule. What is the meaning? Means load of everybody is less than equal to opt. This is less than equal to opt, because this is the best schedule we can think of, right? So now any big job can be placed at one. Okay, fine. Medium job. Can a medium job be placed with a big job? No. So every big job goes. So let's write down this little cutie observations. Okay. So what is this? First, every big job is assigned on different machines. Is that fine? Every big job is assigned on different machines. Okay. Okay. And okay, every big job is assigned to different machines. Do you agree? Right? Okay. Secondly, let's write down second observation. No medium job can be assigned on the machine that has big job. Agreed? Agreed? That's right. Okay. So if you have a medium job, you better have some machine which is empty for it, because suppose these are the machines which we have placed, because they are identical machine, it doesn't matter. First place them big jobs. Now we have some machines left here. So first of all, what did we know? Because of this, Nm better be less than equal to m, otherwise you are dead, right? So, or okay, now tell me how many medium jobs can you assign to a at most two. Excellent. Okay, so this is my observation number 3. Okay, no machine can have more than strictly more than 2 medium jobs. Is that fine? Okay. So can I no, this is wrong, it was n big. N medium is less than equal to how much? How much machine is left after, if I have big NB machine? So how many machines I have left after that? NB. And each of them can have how many machines? How many medium jobs? 2. That's it. Not everybody can have 2. So this is what it is.
If it's all equal, then
Every machine is.
then they're all more than 2 up, so then Pn cannot be.
No, I don't understand what you are saying.
If Nb equal to M, I think Nb has to be less than M.
NB is less than equal to M.
Strictly less than M.
Maybe NB is 0 for all that you care.
If Nb is all,
If NB could also be 0, no?
yeah, I'm
Yeah.
saying Nb should be strictly less than M,
Why?
because if Nb is equal to M, then we have M jobs that are greater than 2 up by 3.
So,
So then Pn cannot be greater than up by 3,
why?
because Pn is the last job, L is N.
So,
So then greater than 2 up by 3 plus greater than up by
What?
3 will be greater than op. Right?
why this is, why there could just be M jobs?
No, what
Wait, why can there be just N jobs and the last job is big job?
No, I'm not saying that.
Huh.
I'm saying there can be, NB has to be strictly less than M, because if number of big jobs is equal to M, then we're assigning M jobs, each has greater than 2 up by 3 running time.
Okay, so
Pn, which is our last job, we
which is at least opt by 3.
Yeah, and we know that that is the last job.
Suppose n is m.
Yeah, so if we have m machines
Huh?
that have greater than 2 opt by 3,
Okay.
and we have at least one job we know that has greater than opt by 3.
Which is also 2 opt greater than. That's all that it says. No, I mean I do not understand your question.
So that last job itself,
With a big job, no?
Oh,
This is exactly what. Last job could be itself the big job.
okay, right.
All it says is strictly more than opt by 3. Right. So if it is, so if it is more than 2 opt by 3, it is still opt by 3. Okay. Okay. So this is all, and so this is all that I can say at this point of time. And because I have assumed Pn is at least opt by 3, what is Pb Ns? Ns is equal to, what is Ns? Pn was the last job, right? If that itself is big,
So there's no NS.
so Ns is 0. Ns is 0. Do you understand? Pj is less than equal to opt by 3. And what was the algorithm? It was largest, 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 and last was the least. If that guy's processing time is strictly greater than opt by 3, is there any small job left? So that is 0. So that's great for us. Is that fine? Okay. Now, what will my greedy algorithm do? Please tell me. So now that I have told everything, what my greedy algorithm will do in this case? First, it is definitely going to assign all the big jobs first, right? Okay, it did. And then it is going to assign medium jobs in the remaining guy. Okay, so it assigns medium jobs. Now, they are strictly bigger than him. So the rest of the jobs will only be assigned here, right? And so we are done. What is the total number of load at any this thing? This is, what is the total amount of load at this point of time? Look, first of all, in this schedule, we are done, right? I first put big, medium, 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 then medium, 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 because medium can't go up. Okay, this is what my greedy algorithm also does, right? First it fills big because their processing time is strictly larger, then it enters into medium, larger, 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 then it tries to place it here 2 at a time, and we are done, because that's all that jobs we had. Okay, so all these are less than opt, so we don't care. Here, how many items did you put? 2 items of length 2 times opt by 3, so it is 4 by 3, and we are done. Right? So what is the load of this algorithm? Load of this algorithm is, load is upper bounded by 2 into medium jobs, which is 2 times 2 opt by 3, which is 4 times opt by 3, and I am done. Okay. Question? What is the last, what is the property of n, Pn? It is the last item. It means its processing time is the smallest. What is its processing time in this case? Read here. It is what? What is the definition of J? Less than, equal to. So there is no such jobs. So Ns is 0, and then we are done. Okay. Okay. So what you can show actually that greedy, which I don't know how to do it, is actually, I mean this is an exercise in the textbook that when you have this, so let me give you an exercise, okay. So all I cared about is proving to you this is a 4 by 3 approximation. So it is a 4 by 3 approximation because of my idea of big jobs, medium jobs, small jobs. Excellent, right? So all I cared about is by doing this bucketing trick, because look at the induction. Look at the induction. Let's try to do induction all over again. And I don't know what the approximation algorithm is. Suppose I did not know what the approximation. There was some approximation algorithm that we create, and where we say, hey, actually the ratio is 1 plus epsilon times opt. My first part of induction will still hold, right? Oh, if it is not the last item this, oh, then what is, so if, you know, I will get to that, and then that is what will lead to us to the next set of directions. Okay. So, okay, so this is the factor. Greedy produces 4/3 factor, induction on jobs, blah, blah, blah. Okay. So, suppose I was trying to prove, not greedy, a future algorithm, okay, a future algo, which we will make in a meter, produces 1 plus epsilon factor approximation for load balancing. Okay. Induction still holds, no? N equal to 1, I just one item, just place it. Okay, if L is less than N, my induction still holds. Okay. So, if I can show is Pn is less than epsilon times opt, I am done. If I could show that the last item is less than epsilon times opt, then I am done. You understand? If I do that same analysis, what was that? What was that same analysis where I wrote opt by 1000? So, I can also write there epsilon times opt. So, if all I can somehow manage to show, say, okay, so if Pn is less than equal to epsilon, we know how to handle. So, I can assume that Pn is epsilon times opt. That is, so what we did here, we made an algorithm for the case when every item was big. I made a handcrafted algorithm, right? Otherwise, my induction works, right? So, all I care about is these small items are waste, forget them. Like, but what is small, what is big? Like this, we need this understanding of definitions, which is very unclear to us at this point of time. You understand what I am saying, right? This is very, very unclear to us at this point of time. Okay, but all I care about is if my last item was less than epsilon time opt, then my this induction hypothesis for whatever that algorithm I make will work. The case which is not going to work when every processing time of every item is big. By big means it is at least epsilon times opt. So, when epsilon was 1/3, I gave you a handcrafted algorithm. Now, let us try to handcraft this algorithm for epsilon, and that is all that I would like to do. You understood the question? Like understood which setting we are in? So, this is why I did this analysis, okay, is okay, that if I substitute 1/3, this analysis work. What will happen if I substituted 1/10? Will this analysis work? How will I do it? Like, it's not clear that why will this analysis work, right? You understand why it will work, okay? But there are some beautiful properties that we use in this analysis, which I will try to tell you in a. So, let's go have coffee. You have a 10 minutes break. That's a good time to take a break. We'll come back in 10 minutes. What's the time? Yeah, it's 10:58. So, we'll come back at 11:15. Okay, and we'll carry on. We'll carry on approximation. We'll not carry on randomization. Okay, I couldn't. Huh?
How long is this class?
I don't know. I'll try to finish by 12.
Okay, take it.
I'll try. No guarantees. But at least you will see all the ideas that we need. This rest is maths, like calculations. Okay.